in the nuclear physics, like some of the important topics which we will try to cover in I think 10 to 12 lectures. And so these are the topics which are part of your GATE 2021 syllabus. So I will not try to repeat all those topics or explain it. So you can download this GATE syllabus and you can check. So we will have a look, or we will talk about each topic, like what are the nuclear forces and various properties of nuclei, binding energy, and then we will discuss various models like liquid drop models, shell model, application of shell model, and then some of the Rutherford scattering, which we will also talk a little bit of in our today's lecture. And then we will discuss about some decays like alpha, beta, and particle decay, theory of radioactivity, and some little bit about the nuclear forces and what type of interaction which exists between these nucleons. And we will discuss in detail about the deuteron problem, some isospin symmetry, and then we will also talk about some particle accelerators, so with which we can accelerate the particles, and some detectors like GM detectors, scintillation detectors. So this is your syllabus of NET GATES CSIR, and almost 95% of the syllabus it is the same as it is in the GATES paper. So more or 2 or 3 topics which are different, like the collective model, which is part of the CSIR syllabus, but it is not mentioned in the GATES syllabus, and 1 or more topic which are not included in the CSIR, like the accelerators and the particle detectors. So here in this picture you can see that I have made a record of the last 10-year CSIR papers from June 2011 to December 2018, almost 8 years. And you can see I have explained in this that what portion of mathematical physics which come in CSIR, what portion of classical mechanics which come in CSIR, electromagnetic theory, quantum mechanics, this is the thermodynamic and statistical mechanics, so this is electronics, so this is atomic and molecular spectra, this is condensed matter physics, and this is the nuclear and particle physics. So you don't need to study these all subject in detail. So your basic idea is to crack CSIR, or either through JRF if you are planning to pursue your PhD, or if you want to clear as a lecturership. So then the catalyst that exists for physics CSIR, that is around 85 to 95. So you need to focus on these much marks which you have to take from 200. Now, how you can take these 85 to 90% marks, that is around, not percentage, so around 45 to 50% if you can take in CSIR, then you can easily crack as a JRF candidate, and you can be selected in one of the reputed institutes where you want to start your PhD. So like in IITs or IISc, you can easily be a selected candidate. Now, if you look at this, so I will discuss atomic maybe in the near time, or if I talk about the nuclear and particle physics, so you can check that in B and C section. So the nuclear part, it is the part of your C section. So around 3 to 4 questions. So every time, so minimum 3 and maximum 4 questions of nuclear physics, they always come in CSIR exam. And 1 question that is of 5 marks. So it means that around 15 to 20 marks paper it is from nuclear and particle physics, that is around 8 to 10% of the whole total percentage. So in nuclear physics, we will not go in so much detail. So because the most of the questions which are related to numerical point of view, so we will try to just give a brief idea about the topic, and then we will have some practice about a good exercise about the numerical problems. So these are some of the reference books which I suggest you to read, so to have a good idea about this nuclear physics. So the important book, that is the Bohr and Michelson book. I have a soft copy of this book I can share with you. And the very important book, that is the Kenneth S. Crane. So all the readers, so they suggest you about this. And it is a very important book of nuclear physics. So second important book of physics, that is the S.N. Kushal book. So maybe you have read this book during your PG, when you are doing PG in physics. And the other book that is more important or more concentrated about the particle physics, they are the Perkins, so which is a book of the high energy physics, and the Introduction to Elementary Particle Physics by Griffiths. So these are two books that is more or less related with particle physics, and the upper three books, they are more or less related with the nuclear physics. So apart from that, I will also provide some notes to you, some shortcuts to you, so you can use during your last time of examination to have a look over this nuclear physics. So in our today's lecture, we will discuss about the development of nuclear physics, how the idea, how the origination of this nuclear physics research, it comes into line, and then we will discuss, have a look about the structure of nucleus, what is the size, what is the density, and if time pertains, then we will also discuss about this neutron to proton stability curve, or otherwise we will discuss in the next lecture. So what are the milestones in the development of nuclear physics? Now the discovery of radioactivity, so like in 1895, scientist Röntgen, so he has discovered the X-rays, and 1 year after, in 1896, Henry Becquerel, he observed that the uranium atoms, the crystals of uranium atoms, they are emitting some sort of radioactive particles, and which are affecting the photographic or photoelectric plates. So these particles, they are coming from these radioactive sources, and after that, Marie Curie, he later in 1898, so he isolated some radium and polonium radioactive ores, and he then published that. So there exists some sort of a higher atomic nuclei which are radioactive, and then they further work on this theory of radioactivity and try to find what type of particles like alpha, beta, or gamma particles which are coming from this radioactive nuclei. Now, so in 1897, so JJ Thomson and his researchers, so they discover a famous tube which is known as the cathode ray tube, and they do see that the discharge of electricity, it takes place through gases. So when they are applying some sort of electrostatic potential to metal plates, and from that, the J.J. Thomson, he tried to find that these particles which are being ejected from this negative electrode, and they are being affected by this electric field. So these are the electrons. So the discovery of electrons, so it kicked up the idea about where from, so these electrons, they are coming from where. So either they are from the atomic region or they are from the nuclear region. So otherwise, before that, so Dalton, it has explained that atom, it is a elementary particle, but the discovery of this electron, it proved the theory of Dalton wrong, and J.J. Thomson, he explained that there are some other elementary particles which exist within the atom. So later on, W. Thomson, he proposed in 1907 the plum pudding model, and he explained about the structure of atom. So this we will also discuss in our today's lecture. So this plum pudding model or the water model, it has been proved wrong by the famous scientist Rutherford, which has explained in 1910-11. So the famous discovery of the alpha scattering, which are being scattered from some sort of heavy body which is existing within the nucleus. And before that, Rutherford, he has discovered some sort of radiations in 2002 and in 1903. So he has explained already that there are some sort of alpha, beta, or gamma radiations which are coming out, and these radiation, they have some adverse effect to the photographic or photoelectric plates. So regarding his discovery, Rutherford, it has been get his Nobel Prize in 1908. And you will be surprised to know that Rutherford done his major important research work after getting the Nobel Prize, because his theory of alpha scattering, it comes in 1911, but he already got the Nobel Prize in 1908. So Thomson, we will discuss what is the Thomson model of the atom. So the J.J. Thomson in 1897, so he made a piece of equipment, so which is generally known as the cathode ray tube, and he made this tube a vacuum tube. So he has expelled all the air from this tube and make it a vacuum, and when he applies some sort of electrostatic plate, electrostatic potential to this from this tube. So just a minute. So you can see that, so when we are applying some strong electrostatic potential on the two sides of this plate, and there is some sort of illuminations. So he has kept some inert gases within this plate like argon or xenon, and when he is applying some sort of high electrostatic potential, and then due to the movement of this current, so these gas particles, so they are illuminating some sort of light, and this gives us the idea. So from this, where this light or this luminescence it is coming, so either there are some sort of photons, so which are being coming out from the atom, or either there's some sort of other structures which are coming out of this atom structure. So what he later did is, so he applied another battery to some other end from where it is collecting those particles. So this is the negative cathode electrode. So he has applied this high voltage, and you will see that some particles which are originated from this negative end, and they are being attracted toward this positive end, and at the positive end he applied another battery, and you can see from this picture that these particles, they are rather moving toward a straight line, so they are being attracted towards the positive end of the another battery. So from this picture he get the idea that the particles which are coming out from this cathode plate, so they are having some charge, and they are being attracted towards the positive end. So you can check, so when we switch on this battery, so some sort of particles which start from this negative end, they are moving toward this positive end. And now when I apply some sort of battery, you can see that he has applied some sort of strong electrostatic field, and the path of these particles, it has been changed. So rather moving toward the straight lines, so these particles, they are collected towards the positive end of the battery. So he found that the moving particles, so which are being attracted toward these particles, so he found it is having a negative charge. So what are the outcomes of this famous J.J. Thomson experiment which he proved? He proved that atom of any element, it can be made to emit tiny negative particles. So atom, it is not a elementary particle. So before the Dalton theory which says that atom, it is the elementary particle and we cannot break it into further. So he proved the theory of Dalton as wrong, and he said that there are some sort of tiny negative particles which are coming out of the atom structure, and from that he concluded that all atom must contain these negative particles. So atom or molecules, whatever the atomic number it has, so these tiny negative particles, it is present in all the atoms. And he said that atom did not have a net negative charge. Now, before his experiment, if you remember the Wilson experiment, Claude Wilson, he designed a cloud chamber, and another Millikan experiment, oil drop experiment. So what they have said that the matter has two opposite charges, positive and negative charges, and they have cited in their research paper that the matter either atom or molecules, so they are neutral, having equal and opposite charge. So same number of negative and same number of positive charge it is present in the atom, and the overall charge on the atom it is considered as neutral charge. So what Thomson suggested that, so there are some sort of another positively charged particle which is also present within the atom and which is keeping this atom as a neutralized particle. So he discovered electrons so far. So later in 1907, so William Thomson, he proposed a model which is known as the plum pudding model, or you can also call it as the watermelon model. So what he proposed in his model that the negative electrons, so they were embedded all across the atom structures, so like a bees, or which, so you have seen the structure of watermelon. So all the fluid, so that is the positively charged particle, and the electron, they are some sort of seeds like a watermelon seeds, so they are scattered randomly all across the atom. So the positively charged, so they are the cloud which is having scattered, or a fluids which is scattered all across the atomic structure. So these are some of the discoveries of Thomson. So they know that the electron it is being emitted from matter. So they proposed this model, in this model, that atom consists of small negative electrons, so which are embedded in a massive positive sphere, and the positive charge it is scattered all across this sphere. So electrons, they are like the currents in a plum pudding model. So the same as plum pudding means, so everywhere, so there are some puddings and there are some plums, or you can say chocolate seeds, or so which are present in something like in a cake. So this is called the plum pudding model of the William model. So another milestone which comes in this nuclear physics field, so in the year 1911, so when Rutherford along with his other researcher Geiger and Milestones, so they try to perform some scattering experiment. So what they established that the nucleus, it could be treated as a point mass and a point charge. So most of the atomic mass it was contained not all across or not around the boundaries of the spherical atom. So while the positive charge it is present within the center of the sphere, and there is some sort of forces, so which has been further not explained by Rutherford, but some sort of Yukawa interactions which has explained in 1920 odds, and which are keeping these nucleons so within this nucleus. So what expression alpha particle, it can interact with this nucleus structure, which is a heavenly positively charged body present within the nucleus. So we will do the derivation of this to find out the value of this d, what is the minimum distance from where these particles, so they get scattered back. So in his alpha scattering experiment, so what other Rutherford explained that the nucleus, it has a relatively small diameter compared with that of atom. So the size of the nucleus, it is of the order of 10 is to power minus 14 to 10 is to power minus 15, as compared to the size of atom, which is of the order of 10 is to power minus 10 meter. And he also explained that most of the mass of this atom, it is concentrated in the center of the atom, which we explained, which he gave the name as the nucleus. Now, how this alpha scattering experiment, so the idea of doing this experiment, it comes in the mind of Rutherford. So in the early days of the atomic theory, so many physics, they are trying to explain the atomic structure, and in the year 902, Rutherford showed that the alpha particles, they are being emitted from some sort of unstable radioactive materials, and these alpha particles, they are being electrical charged, and they are equivalent to helium nuclei, which are moving with a very high speed. So in the year 903, so he also discovered the found the discovery of gamma radiation from some sort of radioactive material. So this discovery of this helium nuclei from some radioactive material, he gives us the idea to shoot out these alpha particle to some sort of a solid target, and he want to check that what happens when a high energy particles, it interact with the metallic body with the solid target. So in 909, Rutherford used these alpha particles which are being emitted from some radioactive material, and he used the composition of the gold foil, so where he want to shoot out these alpha particle. So rather than using a thick gold foil, he tried to use the thin gold foil, because the size of the gold foil atoms, so more or less they are quite bigger as compared to the size of alpha particles. So that's why he want to see that what happens when a lighter body interacts with a heavier body. So this is the experiment which he designed, and the basic aim to design this alpha experiment, alpha scattering interaction experiment, is you want to know when these two atoms, so they interact, so what happens, and how these atoms they break, and how they get scattered, and at which angles. So this is the apparatus. So here you can see that, so the some radioactive source which is being kept within this lead sheet, and this radioactive shot, he is shooting the alpha particle from here, and this is the gold foil, so where these alpha particles, they are being scattered, and they are being scattered at different angles. So the value of this theta, it actually depends at which angle this helium atom, they are interacting with this gold atoms, and on the basis of this, he found that some are being retraced back, some are being scattered at very high angles, some are being scattered at light angles, and he found all those detectors, all those angles with this zinc sulfide detector, so which is a movable plate, and he can move and check at which angle the concentration of this scattered particle, it is higher. So he fired alpha particle through a piece of gold foil and used the zinc sulfide detector to detect these scattered alpha particle and at which angle they are being scattered. And here you can see that a simulation which alpha particle, they are interacting with this gold foils. So these red color, they are the gold atoms, and you can see some alpha particles, they are being ray traced at an angle of 180 degrees. Some are being scattered at some different angles. So from this experiment, or from this experimental results, so he concluded that most of the alpha particle, they are passed through this thin gold foil undeviated. So most of the alpha particle, you can check that they are being traveling from this gold foil, and they move in the straight line without any deviation or without any scattering. So few alpha particles, they are being deflected from their path, but they are continue through the gold foil. So a small number of alpha particles, so they have been rebounded and retraced, at an angle of 180 degree. So another conclusions he explained from this experiment is, as most alpha particle pass through this gold foil atoms undeviated, so Rutherford concluded that most of the atom was actually a empty space. Like in, if you look at this J.J. Thomson plum pudding model, so what they have said is that atom, it is completely filled with a fluid which is having a positive charge, while some negatively charged electron, they are randomly distributed within this fluid. So Rutherford suggested that the atom, it is not actually fully filled with a fluid. Most of the atom, it is a empty space, and the electron which exist within this atomic structure, they are in some having discrete structure or discrete orbits ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਆ ਉਹ they exist within this discrete orbits. So a small number of alpha particles, so they have been rebounded. Why they get rebounded? Because they get collisions with this gold coil, gold atoms. So they have been retraced because the much larger or heavier object they are interacting with, and which contain a concentrated region of this positive charge. So he suggested that some sort of a concentrated body which exists within the center of this atom, and why that's why these alpha particle, they are being rebounded from when they are shooting these alpha particle right in the center of the atom. So he suggested some points from this discovery. So he suggested that atom had a positively charged center which contains most of the mass. So there is some sort of a body which is having a positively charged on it. It exists, or it is present within the center of the atom, and he gave this positively charged body which is present within the atom, he gave the name nucleus. So he further suggested that this nucleus, it was surrounded by this electron in some orbits, and that's why this whole atomic structure, it is completely neutral, because now there are positively as well as negatively charged particles, they exist, and these electrons, so they are moving in some sort of orbits, like the student of Rutherford, Bohr, later on explained this how these electrons, they are present within the atomic structure, and he explained about the Bohr atomic spectra or Bohr atomic model. So this is the very famous model with that's why this Bohr got the Nobel Prize for the discovery of this Bohr atom. So the Bohr was a student of Rutherford. He then did this work to explain further what is how these electrons, they are present within these atomic structures. And further, Rutherford suggested that these electrons, they are not stable, they are moving in some sort of having some energy, and they change their orbits when they gain or when they lose their energy. So if you look at this Rutherford experiment, so he gave the idea of this conservation of energy. So from this conservation of energy, so he drew out a physical picture that this alpha particle, which is having a +2 charge, that is 2 times, because it is structure of helium-4, so it has 2 protons, so that's why he considered it has 2e charge, and m is the mass of this alpha particle. And when these alpha particle, they are moving with this gold foil, so with the kinetic energy, that is E, and these alpha particles, they experience some sort of Coulomb repulsive forces. So these particles, when they move toward this nucleus, and when they come closer to this nucleus, which is a strongly positively charged body, and alpha particle which is also a positively charged, and when this strongly positively charged, it repels this positively charged structure, and that's why it retraces its path, and these particles, they are scattered at different angles. So in this interaction, so total energy, it is always conserved, and the kinetic energy of this alpha particle, it is being converted into the potential energy as these alpha particles, they are approaching toward this nucleus. And he tried to find out the distance, which is known as the distance of closest approach, up to which maximum distance these alpha particle, they can go closer to this nucleus, or this distance from there, that distance they get retraced or they get rebound back, and that distance is known as the distance of closest approach, and they do not move ahead because of the strong Coulomb forces which exist between these two particles. So by equating this, so I will try to do here. So when the kinetic energy of this alpha particle, they are approaching toward this nucleus, so they are converted into potential energy. So if they are moving with the velocity v, and m is the mass of this alpha particle, and this is equal to the penetration energy. So a particle or a helium particle, or later on they done some experiments with the electrons, and they suggested that, so there is some sort of penetration energy which is minimum required by a particle if we want to interact with this nucleus. So this potential energy, so that is equivalent to the penetration energy. So Q1, Q2, so one is 2 times E, second is the ZE. So that Z is the number of protons which are present in this gold foil or any atom they are taking, and D is the distance of closest approach, and from this they can find out the value of this D into 2 over mv square. So this comes out to be Z into E square over 4 epsilon naught into mv square. So for gold foil, Z is 79, the atomic number of gold foil is 79, and this mass of alpha particle, that is 6 into 10 is to power minus 27 kg. And suppose these particles, they are moving with a velocity that is of the order of 10 is to power 7 meter per second. So that is the maximum velocity with which they can travel, because they are very heavier particle. So they cannot travel at a speed of light. So the maximum energy with which these alpha particles can travel, that is of the order of 10 is to power 7 meter per second. And putting these values, so he found the kinetic energy of this alpha particle, that comes out to be 5.486. So if they are moving with this energy, and epsilon naught, that is the permittivity value, it is 8.85 into 10 is to power minus 12. And from that, by putting all these values, you can find out this distance of closest approach if the alpha particle, which is moving with the velocity of 10 is to power 7 meter per second towards this gold foil, and it comes out to be 4.15 into 10 is to power minus 14 meter. And Rutherford then changes his target, and he done some alpha interaction with silver atoms, and then he done with copper atoms. And with copper atoms, so whose atomic number is silver atom, so Ag, so whose atomic number is 47. So this comes out to be 2.47 into 10 is to power minus 14. So with copper atom, So he found this distance of closest approach, that is around 1.2 into 10 is to power minus 14 meter. So the value of this D, it is around 10 is to power minus 14 meter. So from this he suggested that some points. So he concluded that the positive charge of the atom, so they were concentrated in the sphere whose radius was no longer than about 10 raised to power minus 14 meter. So because the maximum distance with which these alpha particle, so the distance between this centrally positively charged body and the alpha particle at a distance, they are being retraced, so that is of the order of 10 is to power minus 14. So he considered that, so if this is the maximum distance, then the size of this atom, it should be size of this nucleus, it should be around 10 is to power minus 14 to 10 is to power minus 15. And so this changes as the atomic number of this nuclei, it is being changed. So he derived this size of this nuclei in terms of femtometer. So he explained that the atom whose size is of the order of 10 to the power minus 10 meter, and the size of the atom, it is much greater as compared to this nucleus, which is a heavenly small body which is present within the center of the atom. So this is all about some sort of interaction. So now you will wonder that, so we generally talk about that the nucleus, it consists of nucleons, and nucleons, that is neutron and proton. And the discovery of this neutron, it is in the year around 1932. So when Chadwick explained about the discovery of neutron, and he gave this name that another particle which is present within this nucleus, and that particle having a neutral charge, and along with that there is some sort of a positively charged particle, so that is proton. So Rutherford in the year 1913, he explained that some sort of positively charged particles which are present within the nucleus. So from this 1913 to 1932 or 35, so there are various hypotheses, various models which comes into line. So I will not go in detail all about that. So like the proton electron hypothesis, so some people are saying that electron which are part of this nucleus, and they are present along with this neutron, along with this protons. So this hypothesis, it got failed, so due to some wave mechanical phenomena. So when the quantum physics, it comes into line, and they found out that the value of this wavelength of this particle, it is very high as compared to the size of these particles. So when the origin of this quantum mechanics, it comes into line, so then these various models, so they get failed. So after that there is a hypothesis, that proton neutron hypothesis. So the idea of this hypothesis, it basically comes in this year 1921, and so people are aware that some other particle which is present within the nucleus along with this proton, and we will discuss how these particles, they interact, like when we will discuss about the nuclear forces, and how these proton and neutron, so they are being present within these nucleus. And we will also talk in the coming lectures about the meson theory of like the Yukawa interaction which exists between these particles, and there is some other particles after the discovery of the quark models, like the muons or the pions. They are also present within these nucleus, which are binding these nucleons closely to make a stable nucleus. and how these proton and neutrons, so they are being changed from one particle to another particle. So when they are exchanging these neutral pions, these positive pions or these negative pions, so we will talk in detail about this meson theory and how these nucleons, so they are interacting with each other within this nucleus in the coming lectures. So talking about the general properties of these nuclei.
बटन बंद करो फिर दिखाने का बड़ा था.
So please mute your mic, Sarika. So what nucleus physics suggests that all nuclei, they are composed of protons and neutrons except hydrogen, because hydrogen, which is having one H1, so there is only one proton and zero neutron which is present in these hydrogen. So except hydrogen, in all the atoms, so there are protons and neutrons which are present within the nucleus, and generally we define the atomic number of a atom with the notation Z. So Z, that is equal to the number of protons which are present in the nucleus, and we define the neutron number with N, so that is the total number of neutrons which are present within the nucleus. So from that we generally gave the atomic symbol to an atom or to any atomic nuclei. So with this notation, where at the bottom we write the number of protons or the atomic number of that atom, and this upper, it represents the total number, the mass number of those atom. So like in the example of aluminium, you can see that the atomic number of aluminium is 13 and mass number is 27, and from that you can find the number of neutrons, so which is equal to A minus Z. So this way you can calculate the number of protons and neutrons which are present within this nucleus. So the number of neutrons is 14, number of proton is 13. So this value of neutron and proton, so it provides a detailed or very important information about the properties of that particular atom. So we will discuss in the next lecture about the stability ratio, that is the NZ curve. So we will try to plot the proton number as compared to neutron number, and you will see that as the number of neutrons, it increases, the stability curve, it is no longer a straight line, and this curve, it is being attracted towards this n value as compared to this p value, so rather than moving straight. So you will also see in the higher atomic nuclei, for example, if you talk about the uranium nucleus, so in 92 having mass number 238, so here number of proton is 92, while this number of neutron, it is very high as compared to this number of protons. So why this number of neutron, it is larger as compared to proton, and how it is impacting? So there are some other models, so some other energy which is the asymmetry energy, that we will discuss in the liquid rock model, and how it is impacting to the total binding energy of these nuclei. So more properties of the nucleus. So the nucleus of all atom, of a particular atom, must contain the same number of protons. So isotopes, isobars and isotones you all are familiar with. So isotopes are those atoms, so having the same number of proton but different A values, and there are various examples of these isotopes. Now if you compare these carbon isotopes, so all these carbon, so they are having same number of protons but different number of neutrons, and with the help of this binding energy, we can also tell that from these four isotopes, which one is the most stable isotope. So that we will also discuss in the liquid drop model. So sometimes there is a question. So all these four options are given, and you have been asked that which one of is among below is the most stable isotope, and from that we can calculate the binding energy first, and then from uh, we will maximize its value, and then from that we can find out which is the stable isotope. So about the isotones, so isotones are those elements which is having same neutron number. So for example, this carbon 613 and this 714, so they are the isotones, so which is having same neutron number. So similarly, you can find out the isobars. I will write it here. So what are isobars? So those nuclei which is having same mass number. So for example, 6, 14 and 714. So these two are isobars having same mass number. So similarly, this concept of this binding energy, it gives the idea about the mirror nuclei. So mirror nuclei are those nuclei having same mass number but with the proton and neutron number interchanged. So what are mirror nuclei? So sometimes there is a question. So find out which are the mirror nuclei among this 6C11 and 511. So mirror nuclei are those nuclei which is having same mass number but proton and neutron number interchanged. And for example, in this case, carbon proton number is 6 and neutron number is 11 minus 6, that is 5. While in this boron, proton number is 5 and neutron number is 6. So proton and neutron number, it is interchanged by one unit. So these two atoms, they are known as mirror nuclei. So another example of mirror nuclei, you can see 7 nitrogen 13 and 6 carbon 13. So again, in nitrogen 7 proton and 6 neutron, and in carbon 6 proton and 7 neutron. So proton and neutron number, it is being interchanged by 1, and those nuclei are known as the mirror nuclei. And these nuclei, so they have quite similar physical properties, and apart from that, the charge on this nucleus, because Rutherford suggested that it is having a strongly positively charged body which is present in the center of the atom, and they represented it as a positive charge E, and the charge on the electron, that is minus of E, and the neutron, which is a neutral particle which is having no charge, and one charge, that is equal to 1.6 into 10 raised to power minus 19 coulomb. So mass of the nuclei, so that we generally find out the total number of proton and neutrons which are present within the nucleus. And here I would like to say that the mass number of nuclei, it is not the same as that of the atomic mass, because the atomic mass, that is the mass of nucleus plus mass of electrons, कि उस एटम दे विच जिहड़े आ किन्ने इलेक्ट्रॉन जिहड़े आ ਉਹ ਪ੍ਰੈਜ਼ੈਂਟ ਹੈਗੇ ਆ, ਸੋ ਉਹਨਾਂ ਦਾ ਵੀ ਜਿਹੜਾ ਮਾਸ ਹੈਗਾ ਆ ਉਹ ਵੀ ਕੰਸੀਡਰ ਕਰਨਾ ਪਏਗਾ। ਹੁਣ ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ ਕੀ ਆ, ਮਾਸ ਆਫ ਜਿਹੜਾ electron that is very less as compared to mass of proton. Now if you check that the mass of proton, it is around 1836 times larger than the mass of electron. So atomic masses ਦੇ ਵਿੱਚ ਜਿਹੜਾ mass of nucleus it is having 99.75% that is due to the nuclear mass, while 0.25% that is due to the electronic mass. And how we calculate this mass? So we calculate these particle masses in terms of atomic mass unit. So 1 AMU that is equal to the mass of the nucleus, which is in terms of atomic mass unit, and 1 atomic mass unit that is equal to 1/12 of the mass of carbon atoms. So that we will compare with respect to this carbon, and from that, by putting these values, I will not derive the expression, so you can find out the value of this 1 atomic mass units, so which comes out to be equal to 1.66 into 10 raised to power minus 27 kg. So from that we can find this energy from this binding energy expression. So that is equal to delta mc square, and delta m that is the change in mass. So when these particles, so they are some sort of nuclear reaction, and this is known as the mass defect, and this is the binding energy. So this we will discuss also in our next lecture. So the energy of these particles we generally represent in terms of atomic mass units, or in terms of mega electron volt over c squares. So 1 electron volt of energy that is equal to 1.6 into 10 raised to power minus 19 joules. So these are some of the values of masses for each particle. Now if you check the value of this proton, so whose mass number is equal to 1.007, and of neutron that is 1.008. So neutron, it is a heavier particle as compared to proton, and you can also see that the mass of electron, which is very less, that is of the order of 10 raised to power minus 4 times less as compared to this mass of proton. And we can also similarly find out the mass of a atom. So for example, the mass of this hydrogen atom, so that
Amrit sir,
yes,
sorry for interruption. Actually, some students are trying to join. Okay, so you have to admit them.
okay,
Okay, yeah. Sorry for interruption.
so just okay. So they can ask, student can also ask me, so if they feel anything in between the lecture. So if you look at this mass of a atom, like if you look at the example of this proton, and in this hydrogen atom, which is having 1 proton and 1 electron, and you can collectively find out the total mass of this atom, and it comes out to be equal to 1.07825. So this includes, so you can find out or compare the value of this proton mass as compared to this hydrogen mass. So that is 0.5 value, it is increased, and that is due to the mass of electron which we have added. So by adding the number of electrons which are present and multiply the mass of these electrons plus adding the mass of nucleus, you can find out the total mass of a atom. So the size of nucleus, so that is we generally find out with this relation, and the nuclear radius that is equal to R0 A 1/3. So where A is known as the mass number, we will try also the 1 or 2 numericals related with this. And this R0, that is the standard value or the average radius of a stable nuclei. So we generally consider that the stable nuclei which is having a spherical shape, and when as the number of protons and neutrons, so they increase the size of this nucleus. It can be a prolate or it can be a oblate, and from that we can relate or we can find out the change in quadrupole movement or change in magnetic movement. So that we will also discuss when we will discuss the shell model problems, so in our coming lectures. So for a stable spherical nuclei, we use this formula. So only for spherical nuclei. And the density of these nucleus, so that we can calculate. So the density that is equal to mass per unit volume, and the mass of nucleus, so mass of nucleus, that is if we consider one nucleons, and that is equal to one atomic mass unit. So that is 1.67 into 10 raised to power minus 27. And suppose there are a number of a, that is the number of proton plus number of neutrons which are present. So this mass, it becomes a into one atomic mass unit. And volume of nucleus, that is if it is a stable spherical nucleus, then we will consider the formula of a sphere, that is equal to 4 by 3 pi r cube. And from that you can find out the density. So density comes out to be mass per unit volume, and mass is a into 1.67 into 10 raised to power minus 27 over 4 by 3 pi into r. Here we will consider that is of the order of r naught a1 by 3. And when you calculate it, so r naught cube into a1 by 3 the cube, so it becomes a. So this a and a get cancelled, and this density of nucleus, it is around 2.3 into 10 raised to power 7 kilogram per meter cube, and this is very very high. So you can find out the particle density from this. So the nuclear particle density, if I try to find, and then from that you can find out the value, or you can judge that. So how heavy or how dense a nucleus it is. So the nuclear particle density, so that is equal to the nuclear mass density over nuclear mass. So the nuclear mass density which we have derived, that is of the order of 10 raised to power 17 kg per meter cube, and the nuclear mass, that is equal to 1.67 into 10 raised to power minus 27 kg, and it comes out to be 10 raised to power 44 nucleons per meter cube. So this is a very huge number. So how dense a nucleon is, so you can have an idea that how many number of nucleons they are present in per meter cube volume of a nucleus. So this is all about for today's lecture, and now related to that we will do some numerical problems. So let us check the first problem, which is in the NET 2011 examination. Now it says that the radius of copper nucleus, it is measured to be 4.8 into 10 raised to power minus 13 centimeter, and we have to find the radius of this magnesium nucleus. Now, as I have explained to you that the radius of a spherical nucleus, we use this formula r naught into a1 by 3. So radius of copper, it is given, radius of magnesium that we have to find, and it comes out to be mass of copper over mass of magnesium power 1 over 3, and mass of copper, so you can check from here. So this represents the A. So mass of copper, that is 64 over mass of magnesium, that is 27, and from that radius of copper that is given, and from this you can find out the magnesium. So this radius of magnesium, so it comes out to be, so they get cancelled, so they are 64, it is a cube of 4, and 27, it is a cube of 3, so this becomes 4 by 3 into 1 over 3, so they get cancelled, and this is equal to 4 by 3. So radius of magnesium, so it comes out to be 3 by 4 into radius of copper, and by putting these values you can find it comes out to be 3.6 into 10 is to power minus 13 centimeter. And you can see that option C is the correct option. Now in the second part of this question, so what they have asked is the root means square energy of a nucleon in a nucleus of atomic number A, how it varies. So we have to find the energy relation with this mass number. So here I would like to say that, just a minute. Okay, so let me erase it. So then we will try to solve there. So in this second part, so the ground state energy of a nucleon, so that is equal to P into C square plus the total rest mass energy of a nucleus. And from this, so the value of this E, it comes out to be P square C square plus M naught square C power 4, where M naught C square, that is the rest mass energy, and from this you can see that the energy, it is directly proportional to P. And using the Heisenberg uncertainty principle, so which says that the position and momentum, so they cannot be same at the same time, and he derived this relation, so that is the famous quantum physics. So the particle, so its momentum and its position, it is changing with respect to time, and delta x into delta p, it should be of the order of h bar, and from that delta p, it is equal to h bar over delta x. Now here is a trick. So delta x, how we can find? Now if you talk about a nucleus, so suppose it is having a radius r, and the probability of existence of the nucleons within this nucleus, so maximum it can be of the order of 2r. So anywhere it can exist. So the value of delta x, so until these nucleons, so they are in the bound state or they are present within the nucleus, so it is of the order of 2r. So here we consider the value of delta x, that the maximum change in position of these nucleons, so it is of the order of 2r, and r is the radius of nucleus, so which is of the order of r naught a 1 by 3, and from that you can see that the delta p, it is directly proportional to a minus 1 by 3, or it is inversely proportional to a 1 by 3. So this is one relation, and this is another relation. So it is directly proportional to momentum, so energy will be directly proportional to minus 1 over 3. So you can check these relation. So option C is the correct option. So moving towards the next problem, so that is came in the Tata Institute of Fundamental Research Examination. So this is also a very famous research institute. So for those research aspirants, so which want to do research, do further research, so it has many branches, TIFR, so you can move like in Park, Baba Atomic Research Center, that is in Trombay in Bombay. So you can be shifted to CAT, so that is in collaboration with this Park. So CAT is also a famous research institute, so which is doing some sort of high energy physics. So this institute is present in Indore. So you can do PhD in these institutes through these TIFR examinations. So a proton is accelerated to a high energy E and shoot at a nucleus of oxygen. In order to penetrate the Coulomb barrier and the surface of oxygen nucleus, the value of E it must be at least. But what the problem is saying, so we are shooting protons to oxygen nucleus and we want that they get penetrated within this oxygen nucleus. Now in order to get this penetration, what will be the minimum energy which is required for this proton, and how we can calculate? So as I have explained, so as one particle it is approaching the another particle, the kinetic energy of that particle it is being changed into the potential energy, and the penetration energy or the potential energy, so that is equal to Z square over 4 pi epsilon naught R. And for oxygen, so Z is 8. So putting these values, E is 1.6 into 10 is to power minus 19 square over 4 pi epsilon naught. You can directly put its value, that is of the order of 9 into 10 is to power 9 into R. So R is equal to R naught A 1 by 3. A is the atomic mass. So atomic mass of oxygen, that is 16. So, and R, that is equal to 1.2 femtometer. So R into 1, you can see 16. Just a minute. So it is equal to R. So this comes out to be 16 1 by 3. Okay. So when you solve this, the penetration energy, so it comes out to be of the order of 3.4 into mega electron volt. So when you find out this value and you divide it with 1.6 into 10 is to power minus 19, then this joule energy it is being converted into electron volt. And when you further divide it, mega electron volt is 10 is to power 6 electron volt. So you can find out the value of this penetration energy in terms of mega electron volt, and this is the minimum energy that a proton must have if he want to interact with this oxygen nucleus. Now, which one is the most option which is close to our results? So 1.8 mega electron volt, which is less than this, so it cannot be correct. So this is very less, 45 kilo electron volt, so it cannot be 180 electron volt, that is very less. So 3.6 mega electron volt. So the proton must have a energy greater than this penetration energy if he want to interact with this oxygen nucleus. So our correct option is option A. So next question is the stable nucleus that has 1/3 the radius of osmium nucleus. Now osmium, so whose mass number, that is 189, and atomic number I think it is 76, and so here we will use the radius formula. So we have to find the nucleus which is having 1/3 of the radius of osmium. So let us say I compare these two values with A1 over A2. So one radius, so that is our osmium, which is 3 times the radius of whose mass number which we have to find. So mass number of osmium is given, and from that we can find the mass number of other nuclei. So this 1/3 goes the other way around, so it becomes power of 3, and you get this relation. So that is 27 A2, that is equal to 189, and from that you can find out the mass number of another nucleus which is 1/3 of the osmium radius, and it comes out to be 7. So the value of mass number 7, that is of lithium. So that is our correct option. So the last question for today's lecture, so that is the volume of a nucleus in an atom that is proportional to which option? Now what is being asked कि ਜਿਹੜਾ ਸਾਨੂੰ volume ਜਿਹੜਾ ਆ volume ਜਿਹੜਾ ਆ ਉਹ ਕਿਹਦੇ comparative ਜਿਹੜਾ ਆ ਉਹ ਹੋਏਗਾ. So how you can find out? Yes, any idea? Dear students, can anyone tell me?
Proportional to the number of nucleons.
Yes.
Mass number?
Yes. Yes. So volume, that is equal to 4/3 pi into r cube, and r, that is equal to r naught into a1/3. So v comes out to be 4/3 pi into r naught a1/3 the power 3. So it comes out to be 4/3 pi r naught 3 into a. So volume, it is directly proportional to the mass number of nucleus. So option A is the correct option. So here you cannot write the proton number because the nucleus which is having proton and neutron which are present within the nucleus. So one more question is there. The mean momentum of a nucleon in a nucleus with mass number, it varies as. So I think the same problem which we have already discussed. So any student can also guess?
Option D.
D? Yes. So the momentum of a nucleon in a nucleus, it varies inversely proportional to a1/3. Now how you can calculate? So that we have already derived. So delta x over delta p. So using the Heisenberg uncertainty principle, and from that you can find out h, that is delta p, which is h bar over delta x. So delta x, so that can have a maximum value which is of the order of 2r, and from that putting the value of r, so you can find out r naught a1/3. So delta p, it is inversely proportional to a1/3 or directly proportional to a minus 1/3. So these are some of the questions. So in order to give a flavor what type of questions which can come related to this the starting topics of nucleus, and this is the assignment for today, and you must try these questions, and there are some questions which are related with binding energy, and some questions which are related with electron proton hypothesis, some questions which are related with the packing fraction or the binding energy of nucleons and how it varies. So we will try to cover the topics in our next lecture about the neutron proton ratio and the binding energy curve. So that is very important question or very important topic in nuclear physics. So I will share this slide also with you, and in our next lecture we will also discuss these problems along with the topics which we will discuss on that day. So any doubt, any question from today's lecture, you can ask me.